Hello learners. Let me start with a simple thought. Imagine drinking fresh juice that hasn't been filtered. It would be full of pulp, seeds, and dust. Not very enjoyable, right? In chemistry, too, when we prepare or extract an organic compound, it often comes with impurities like dust particles, colored byproducts, solvents, or salts. To correctly measure its melting point, boiling point, or even molecular weight, we must have it in pure form. Purification techniques take advantage of differences in properties like solubility, volatility, or adsorption. The trick is simple. The right method depends on the kind of impurity and the nature of the compound itself. Just like you wouldn't use a sieve for salt in water, you must match the purification method with the impurity present. Now, let's begin with sublimation, the magician's trick of chemistry. Some solids, when heated, skip the liquid state and directly turn into vapors. Examples are camphor, anthracene, and naphthalene. When we heat such a solid, the pure compound escapes as vapor and condenses on a cold surface, leaving behind sand, salts, or other non-volatile impurities. Picture it like incense burning in a room. The solid stick produces vapors that settle elsewhere, leaving ash behind. Sublimation is fast, clean, and especially useful in labs to purify aromatic solids. But remember, this is not distillation. Distillation is for liquids, while sublimation is strictly for volatile solids. Have you ever seen sugar crystals forming inside a supersaturated syrup when it cools? That's crystallization in action. This technique relies on differences in solubility. An impure organic solid is dissolved in the minimum amount of hot solvent. On cooling, the desired compound crystallizes out because its solubility decreases at lower temperatures, while impurities stay dissolved or are filtered away. If the compound is colored, activated charcoal is used to adsorb the unwanted pigment. With repeated crystallization cycles, purity increases though yield may fall. The key challenge is choosing the correct solvent, one in which the compound dissolves when hot but not when cold, and in which impurities behave differently. A wrong choice means losing both impurity and compound together. Next, let's talk about distillation, the most famous separation technique. Distillation works because liquids have different boiling points. In simple distillation, we separate a volatile liquid from a non-volatile solid or from another liquid if their boiling points differ by more than 25 Kelvin. If the boiling points are close, we use fractional distillation, where a fractionating column provides multiple condensation and vaporization steps. This is how ethanol is separated from water. For compounds that decompose at their boiling point, we use distillation under reduced pressure, where lowering the pressure lowers the boiling temperature. It's like cooking rice faster in a pressure cooker by adjusting the pressure. Each form of distillation is chosen carefully depending on the liquid's properties. Now here's a clever twist: steam distillation. Imagine you want to distill a liquid that boils above 373 Kelvin and may decompose if heated that high. What do? You send in steam. The vapor pressure of steam combines with the vapor pressure of the organic liquid, lowering the overall boiling point. As a result, the compound distills at a temperature below 373 Kelvin, safe from decomposition. This method is perfect for extracting essential oils from plants like clove or eucalyptus and for purifying aniline. The distillate is a mixture of water and organic liquid, which can be separated later using a separating funnel. Steam distillation is a gift for fragile molecules that hate high heat. Sometimes the impurity is water-soluble and your organic compound is not. Enter differential extraction. The aqueous solution is shaken with an organic solvent such as ether in a separating funnel. Since ether and water don't mix, The compound moves into the ether layer while the impurities stay in the water layer. We then separate the two layers neatly. When the problem is more complex, we bring in chromatography, the detective of chemistry. In column chromatography, components of a mixture move at different speeds through a column packed with adsorbent, separating into bands. In thin layer chromatography, a spot of mixture separates on a coated plate. These methods not only purify but also identify compounds. Just like a coffee filter separates flavor notes, chromatography sorts molecules based on how strongly they stick to the adsorbent. Finally, let's see purification in action with a classic example: separation of ethanol from water using fractional distillation. Ethanol boils at 351 Kelvin, water at 373 Kelvin. When the mixture is distilled through a fractionating column, ethanol vapor rises first and enriches with every condensation vaporization cycle inside the column. What we collect is nearly pure ethanol, which can then be checked by its sharp boiling point. That's the beauty of purification, a mixture of two liquids transformed into a pure product, ready for industrial use in beverages, fuels, or sanitizers. To wrap up, purification methods: sublimation, crystallization, distillation, steam distillation, extraction, and chromatography are the foundation of organic chemistry labs. Always remember, a pure compound is like a true friend, reliable, consistent, and trustworthy. Without purity, every measurement, every analysis, and every application loses meaning. So, purification isn't just a technical step, it's the heart of accurate chemistry.